Okay, here we go. Continuity at a point. With piecewise functions, definition of continuity at x equals c, that's a point. Continuity at a point. But this is how functions are, if functions are continuous, then they have to be continuous at every point. So that c could be anything it wants to be. But here it is. Here's the three ducks of continuity at a point. So if f of x is continuous at x equals c, then 1, 2, 3. 1, f of c exists. The limit as x approaches c of f of x exists, and the linchpin is number 3. The limit as x approaches c is the same thing as the function's value at point c. Of course, we've been working mostly on the second rule of continuity here, where the limit from the left has to equal the limit from the right. So as you're working on that second piece, make sure that the limits from both sides are the same thing. This will be very key, especially when we get to piecewise functions today. Okay, I'll try to get a little more excited here. Here we have 3 tasks we have to do. I've given you a piecewise function. Take a look at this example, which I've numbered 4, but it doesn't really matter what number it is. The only example I'm going to give you today about this. Alright, notice this piecewise function has 2 pieces. Alright, that very top piece for x is less than 2, which is an absolute value function. And the second piece for those x's which are greater than or equal to 2 of a parabola that should face down because of that negative x squared. So our first task here is to find the value of a that would make each piecewise function continuous. So basically our task is to find what constant a in the top and bottom function there would make these 2 functions meet at x equals 2. Okay. The second and third task is basically making sure that this works on our graphing calculator. So we're going to confirm our answers by graphing the function on our calculator. We're going to rewrite the function and provide a sketch on the coordinate plane provided. So just a sketch once we put it into our calculator. Okay, so here we go. What does it mean to be continuous as far as a piecewise function? Well, it basically means that as x's approach 2 from the left-hand side, they're using this absolute value function. Okay, so absolute value has, it could be a v that's pointed up, it could be a v that's pointed down, alright, but it all depends on what that value of a is. Okay. Maybe it's positive, maybe it's negative. If it's positive, then we're talking about an upwards v. If it's negative, we're talking about a downwards v. Okay. We've got to make that particular function meet up with this parabola, which is definitely a downwards parabola because of that negative coefficient. But again, it's got that same coefficient a on the second term. So what is that value of a that makes these functions continuous? Because there is one value of a that will make these things meet at x equals 2. Okay. So continuity at x equals 2 really depends on what these functions, these 2 functions, are approaching as we get closer to 2. So we are basically going to make sure the outputs of each function at x equals 2 are the same. The outputs of each function at x equals 2 are the same. Outputs are just a y value. Functions have inputs. We're going to input the value of x equals 2 and hopefully come up with a value for that constant a, which is the coefficient of our absolute value on the top function and the coefficient of our linear term in the quadratic. Okay, here we go. Let the fun begin. We've got to make sure that the outputs of these 2 functions the outputs of these, the absolute value function and the quadratic, are the same at a particular point. We're most concerned about at x equals 2. We need to make sure these functions are equal. The output of the left is the same as the output of the right at x equals 2. So let the fun begin. We're looking for a, so let's keep that a. We're going to plug in x equals 2, the absolute value of 2 minus 1, plus 3. Is that equal to negative 2 squared plus a times 2 minus 1? Okay? Hopefully you can do your algebra faster than I do. This a times the absolute value of 2 minus 1 is just a. Plus 3. Over here we've got a negative 4 plus 2a minus 1. Okay? I'm going to subtract a, so we've got an a over here. If I add the negative 4 and negative 1, I get negative 5. I add it across, I get a equals 8. Huh? Okay, so what this means is that we've got a value of a, which is 8. So I'm going to rewrite this function. Put it in the calculator. If you don't have your calculators out, please get them out now. Open up a calculator page and define a function. You got to put a little colon equals, making sure that you're using the control frequently used template button to get that colon equals to define a function. Okay. If you've forgotten where all the templated stuff for a piecewise function, for absolute value, for quadratic, for all that stuff, that is going to happen in the next slide. So here in the next slide, make sure you're looking at the frequently used template button. You'll get your absolute value. Here is where you will get your two-piece piecewise function. Make sure you're using this particular box for the two-piece piecewise function. Some of you guys are used to that. Some of you guys were doing this one, which is not the one we want. We want to make sure that you are using this button for your piecewise function. Okay, that gives us the function and domain template there. Okay, in the end, once you get that piecewise function defined in your calculator page, go ahead and enter a new page, a graphings page, and go ahead and graph f of x on there. And you can see that we have this absolute value function for x's that are less than 2. Okay, and then at the point of 2 it changes to that negative parabola. And those happen to meet to be a continuous function at the point 2, 11. If you remember how to put a point on your function, if I go through the steps, I think you go to menu, go to geometry, and then go to the point on tool. You can get that point that I'm talking about here, and you can move it to x equals 2. You can move it around the function as well. And yes, Andres, I'm going to tell you how to put that point on the x-axis to get that dependent point. But for now, let's just put an independent point on the function just to make sure you can move it around there and make sure it's continuous with your graph. And that's about it. You guys are going to practice about 6 times, and use your graphing calculator to confirm. Make sure those pieces meet, and as you sketch it on your paper, try to highlight that point at which they meet. And this point, it would be at that 2, 11. All right. Happy graphing and finding constants to make things continuous.